Today is an introduction to matrix methods for systems of linear differential equations. And to start off with, we're going to look at a system that we know how to solve. We're going to solve it, and then we're going to look at the equivalent matrix form. So let's start with the system x dot equals 2x plus y dot equals x plus 2y, and we'll use the methods we've talked about before. We move everything onto the left-hand side, and then we write things in terms of operators. X dot is d, minus 2x is the minus 2, so d minus 2 acting on x is the same as x dot minus 2x. We have our minus y. We do the same thing with the other equation where we get y dot minus 2y minus x equals 0. We put the minus x with the x terms, and then y dot minus 2y is d minus 2 acting on y equals 0. Now we treat the operators just the way that you would treat constants. So what we would like to do is cancel this d minus 2y. So we're going to act on the top equation by d minus 2, which is going to give us a d minus 2 squared x minus d minus 2y equals 0. We have minus x plus d minus 2y equals 0. You add the two equations and you get d minus 2 squared x minus x equals 0. That's the operator d squared minus 4d plus 4x minus x. And when we do everything, that's x double dot minus 4x dot plus 3x, which is 4x minus x, equals 0. The characteristic equation here is r squared minus 4r plus 3. And that factors as r minus 3 times r minus 1 equals 0. So our roots are 3 and 1. And we know that that corresponds to x equaling c1 e to the 3t, that's the 3 root, plus c2 e to the t, that's the 1 root. Now popping up to here, we can see that this differential equation tells us that y is going to be d minus 2x. So back down here, d minus 2x equals y. X we know is c1 e to the 3t plus c2 e to the t. And now we just apply the operator. The d operator takes the derivative. So we're going to get a 3c1 e to the 3t. And we're going to get a c2 e to the t. The minus 2 just is minus 2 times what you've got. So you've got minus 2 c1 e to the 3t plus c2 e to the t. When you combine all of that stuff, you've got c1 e to the 3t minus c2 e to the t. Now, written in column vector form, that's xy is the x, which is c1 e to the 3t plus c2 e to the t, y c1 e to the 3t minus c2 e to the t. Now we regroup that stuff as two column vectors, c1 e to the 3t, c1 e to the 3t, plus c2 e to the t minus c2 e to the t. And now you can factor out a c1 and an e to the 3t in the first one, and we've got c1 times the column vector 1, 1 times e to the 3t. Here we're thinking of that as scalar multiplication, plus c2 times 1 minus 1 times e to the t. And now if we think of u as x, y, and u1 as 1, 1 e to the 3t, u2 is 1 minus 1 e to the 3t, we see that u is c1u1 plus c2u2. And per usual, what we're getting here is the general solution u as an arbitrary constant times a special solution u1 plus another arbitrary constant times a special solution u2. And that's the strategy that we're going to be following for all of this stuff. And u dot can be thought of as x dot y dot. And here's our system, 2x plus y, x plus 2y. So x dot equals 2x plus y was our first equation. Y dot equals x plus 2y was our second equation. And because what we know about matrices, we can recognize that 2x plus y, x plus 2y is just 2, 1, 1, 2 times xy. And we think of this as the matrix A. And now we have u dot is a u. And here we've got u dot as x dot y dot, which is the standard definition for what it means to take the derivative of a column vector. And the next thing to do is let's check using this notation that u1 is actually a solution to u dot equals au, and we're going to do that directly. So u1 is 1, 1 e to the t, which when you multiply that out is just e to the 3t, e to the 3t. So when you take the dot of that, the derivative of e to the 3t is 3e to the 3t, the derivative of e to the 3t is 3e to the 3t, and you just factor the e to the 3t out as a scalar, and you've got 3e to the 3t is u1 dot. Now, what's au1? Well, it's a times 1, 1 e to the 3t, because that's u1, which is e to the 3t, which I'm just using now as a scalar and factoring out in front, times a, which is 2, 1, 1, 2 times 1, 1. And now if you do that calculation, 2, 1 dotted with 1, 1 is 2 plus 1 or 3. 1, 2 dotted with 1, 1 is 1 plus 2 or 3. So we're getting e to the 3t times the vector 3, 3. And if you notice, that's exactly equal to u1 dot. So what we've got is u1 dot equals au1. That's an identity. And that means that u1 dot equals au1, and you have a solution to the differential equations, because substituting in u1 produces an identity. Now we want to check to see that u2 is a solution, and the idea is exactly the same. u2, if you recall, was 1 minus 1 times e to the t. We've just multiplied the e to the t in. So when you take the dot, or the derivative of e to the t is e to the t, the derivative of e to the t is e to the t, and now when you factor the e to the t out again, you got 1 minus 1 e to the t. Now a times u2 is 2, 1, 1, 2 times 1 minus 1 e to the t. The e to the t just sits there as a scalar, and we do this matrix multiplication, and we get 2, 1 dotted with 1 minus 1 is 1, and 1, 2 dotted with 1 minus 1 is minus 1. So a times u2 is 1 minus 1 e to the t, which is exactly what u2 dot is. So u2 dot equals au2 is an identity. Now, what about building solutions from these individual pieces? So we wrote at one point u equals c1u1 plus c2u2. And now I want to talk about this generally. So u1 is not going to be our specific solution here. It's going to be generally x1, y1. And u2 is generally going to be x2, y2, which means that u dot is going to be the derivative of c1, x1, y1 plus c2, x2, y2. You just combine terms, you get this. Now the way you take a derivative is you take the derivative of each individual term. So we're going to get c1, x1 dot plus c2, x2 dot, c1, y1 dot plus c2, y2 dot. And now we can rewrite that as c1 times x1 dot, y1 dot plus c2 times x2 dot, y2 dot. And that's c1 u1 dot plus c2 u2 dot, where this is u1 dot and this is u2 dot. Now, u1 dot is a solution, which means it's au1, and u2 dot is a solution, which means it's au2. So I can substitute for u1 dot and u2 dot, and I'll get c1 au1 plus c2 au2. Now, matrix multiplication is linear, so this is a times c1 u1 plus c2 u2, which is just au. And what we've discovered here is that u dot is au. That's an identity, which means that this is a solution. So we can take linear combinations of solutions and get a solution. So for a 2 by 2 system, that's going to be our plan. Find u1 and u2 independent solutions somehow. And then we're going to build our general solution as u equals c1 u1 plus c2 u2. Now, how do we handle initial conditions? So in this situation, back to the solutions we have before, let's assume that x naught is 4 and that y naught, or y at 0, is 3. Okay, so that means that u of 0 is 4, 3, and u is c1 u1 plus c2 u2. Remember that u1 was 1, 1 e to the 3t, so when you put in t equals 0, you're going to get 1, 1 e to the 0. Remember that u2 was 1 minus 1 e to the t. You put in t equals 0 and you get 1 minus 1 e to the 0. So we end up then with 4, 3 is equal to c1 times 1, 1 plus c2 times 1 minus 1. Combining the terms, that's going to get you c1 plus c2 in the first component. That's going to get you c1 minus c2 in the second component. That's got to equal 4, 3. Another way we could write that is to realize that c1 plus c2 is actually 1, 1 dotted with c1, c2, and c1 minus c2 is 1 minus 1 dotted is with c1, c2. So this is the matrix of coefficients. That's got to equal 4, 3. And now we look at the augmented matrix where we think of it's 1, 1, 1 minus 1. That's the matrix of coefficients where we think of the first column is the C1 column and the second column is the C2 column. And now we're just going to do row reduction, Gauss-Jordan elimination. We've got a leading 1 in the first position, so we're just going to subtract the first row from the second row. 0 minus 2 minus 1 ends up being the second row. Now we want a 1 here, so we divide by minus 2, and we get 0, 1, 1 half. And finally now we subtract row 2 from row 1 to get rid of that 1. And what we end up with here is 1, 0, and then 4 minus a half is 7 halves. What you can read off here is that C1 is 7 halves and C2 is 1 half. And going back to our original solution, C1 is 7 halves, 1, 1 e to the 3t. C2 is 1 half, 1 minus 1 e to the t. And if you want to combine those, you can get 7 halves e to the 3t plus 1 half e to the t, 7 halves e to the 3t minus 1 half e to the t. That's the x solution. That is the y solution. Okay, so finally, let's have a look at a little bigger system. Okay, this time, u dot is AU, where A is actually a 3 by 3 matrix. And now the question is, for what value of k is u1 equals the column vector 1, 3, 2, e to the k a solution? Now, don't worry about where I got the column vector minus 1, 3, 2. That's a topic for another class. But let's assume we've got this thing. We want to figure out for what value of k it's a solution. So the way you do that is you take u1 dot, which is going to be minus 1, 3, 2, times the derivative of e to the kt, which is k e to the kt. And that ends up giving us minus k, 3k, 2k, e to the kt as u1 dot. Now calculating AU1, we just need to multiply our matrix of coefficients times our solution. The e to the kt is a scalar, so the only thing that happens is this 3 by 3 multiplies this 3 by 1, and we take a dot product. Minus 3 times 1 is 3, minus 1 times 3 is minus 3, so 3 minus 3 is 0, and minus 1 times 2 gives us minus 2, so this component is a minus 2. Now carrying out that same dot product, but now with the second row, 4 dotted with minus 4 times minus 1 is 4, 4 times 3 is 12, 12 minus 4 is 8, and then 1 times minus 2, 8 minus 2 is 6, so we get a 6 here, and finally 4, 2, 1 dotted with minus 1, 3, 2 is minus 4 plus 6 plus 2, which gets us 4. So AU1 is minus 264 times e to the kt. We set those things equal. Minus k, 3k, 2k times e to the kt has to equal minus 264 e to the kt, and pretty clearly k equals 2. And that gets us a solution. So minus 1, 3, 2 e to the 2t solves this differential equation. So finding this u1 directly from u dot equals au is harder. And that's what's going to be happening next. And it's not going to be just one class, because there are a variety of cases we're going to have to consider.